Hi, welcome to Calculus. Today we're going to take everything that we've learned so far about infinite series and we're going to apply it to something called a power series. So we're going to be looking for convergence for these things that are called power series, and we'll talk about that here in just a second. And to find that, we can use a lot of the tests that we already know. We can use the ratio and root tests. The ratio test is going to be an example that I have. We can use what we know about geometric series. So let's get started. Power series is anything of this form. The sum from n equals 0 to infinity of c sub n times x minus a to the n. And you can see I wrote out some of that sum. And the important thing here is that a and all the c's are constants. Okay, so a is going to be the center of our series, if you will. So as an example, here I have written out I've written out a series. 1 minus 1/3 x minus times x minus 4 plus 1/9 times x minus 4 squared, and then all the way out to negative 1/3 to the n times x minus 4 to the n. Now, one thing to be really careful of, make sure that your powers work. So if n is 0, we get a positive term because the negative goes away, and sure enough, if n is 0, we have a positive 1. So this is a power series centered at a equals 4, and we've got constants 1, negative 1/3, 1/9, all the way out to the nth one, which is negative 1/3 to the n. Now, importantly, this is a geometric series. We can see it because we have 3, 9. We're doing powers of 3 here for our constants, as we're doing powers for our binomials. So this is a geometric series with a, first term, as 1, and our r, the number that we're raising to power, or the thing that we're raising to powers, is the opposite of x minus 4 over 3. So for that, I just combined these two things together into one piece. Okay, my negative 1/3 to the n, x minus 4 to the n. So my r to the n is this whole thing. And so what's nice is we know a lot about geometric series. We know that they converge when the absolute value of r is less than 1. So this one converges if x minus 4 over 3 is less than 1, which means it converges when x is between 1 and 7. Notice it's centered very nicely at 4 with 3 units on either side. And so we have what's called a radius of convergence. And because it's a geometric series, we can even say what this series adds up to. This series, its sum is 1 over 1 minus r because it's a geometric series. And that is equal to 1 over 1 plus x minus 4 over 3. So I just use the negative here from the r to change this to a plus. And then if you do a little bit of work here in the denominator to rearrange it to combine your 1 and your x minus 4 over 3, then you can turn this all into 3 over x minus 1. And so what we have is that this power series is a wonderful approximation for the function 3 over x minus 1. And so let's keep going, and we have more to look at. But that's kind of one of the things we're going to do with power series. We can use them to approximate functions, and that's kind of slick. So let's get some more stuff on the board. All right, so continuing on, let's look at this series here. We want to know for what values of x does the sum n equals 1 to infinity, negative 1 to the n minus 1 power times x to the 2n minus 1 over 2n minus 1 converge. And this is equal to this sum here, x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. You can convince yourself that those terms work. So what I want to do here is I want to use the ratio test, and so it's going to take me a minute to get to using it. But the ratio test, remember, uses consecutive terms and the ratio between them. So I'm using u here to represent the terms, and I'm going to do u sub n plus 1 first and clean that mess up, and then you can see, then I'm going to go over there and do the ratio test. So u sub n plus 1, now, one other thing. Importantly, the ratio test has an absolute value, so all these negatives are just going to disappear. So I'm going to pretend that they don't exist because they're all going to cancel out. They're all going to drop out here in a minute anyway. All right, so I have x to the 2, and instead of n, I have n plus 1 minus 1. all over 2 times, again, n plus 1 minus 1. And then if you clean those up, you just get x to the 2n plus 1 over 2n plus 1. So now to do the ratio test, I need the absolute value of u sub n plus 1 over u sub n. Well, that's what I just found, x to the 2n plus 1 over 2n plus 1 over the terms of our actual series, x to the 2n minus 1 over 2n minus 1. Since we're dividing with fractions, I flip and multiply, and that gets me here. Now, I need to try and simplify this if I can, so I can figure out where it converges. And for me, what I recognize right away is that I have these x to the 2n's here. One of them has a plus 1, one of them has a minus 1, but that gives me something I can work with. So x to the 2n plus 1 is the same as x to the 2n times x for that plus 1, and x to the 2n minus 1 would be x to the 2n times x to the negative 1. And so then what happens is very nicely those x to the 2n's drop out, and if you bring that x to the negative 1 back to the numerator, you just get an x squared. So I'm left with this, 2n minus 1 over 2n plus 1 times x squared. To finish up my ratio test, I have to take the limit of this as n goes to infinity. But if I do that, x is essentially a constant in this because it's not an n. So the limit here of the fraction is just going to be 1. You can convince yourselves of that. Just divide all 4 pieces of it by n and see what happens, but you're going to get 1 out of it. So we get 1 out of that, so the limit of this is just the x squared. All right, so now we're basically done. The ratio test tells us that something converges if what that limit is equal to is less than 1, or if its absolute value is less than 1. So this converges if the absolute value of x squared is less than 1. That's the same as if its actual absolute value of x is just less than 1. So we have our radius of convergence. It's 1, and there we go. Very nice. Now, importantly, the radius of convergence, it can be finite. In this case, our radius is 1. This would be a capital R here. We can have that R is infinite, and that just means it converges everywhere. And it's possible to have R just equal to a number. If your radius is just a single number, that's the only place it converges. So for this one, it converges for whenever x is between negative 1 and positive 1. If this were R equal to 1, it would only converge if x was 1. All right, so, all right. Yeah, let's get another board. Okay, so let's talk about a couple more things. We have just 3 more things, really. Let's talk about multiplying these series together. So if a of x is sum n equals 0 to infinity of a sub n x to the n, and b of x is n equals 0 to infinity b sub n x to the n, a of x times b of x is equal to sum n equals 0 to infinity of c sub n x to the n. Importantly, this is going to converge in the same place as these two guys did. Okay, these have to have the same radius of convergence. So this will have the same radius of convergence that those two did. Now, the c sub n's, they're kind of a mess. You're probably not going to want to have to ever try and figure them out because they're just disgusting. Basically, c sub n is a sub 0 b sub n plus a sub 1 b sub n minus 1 plus a sub 2 b sub n minus 2 all the way out to a sub n b sub 0. Basically, you do the subscripts going in opposite directions for the a's and the b's, and you just keep multiplying them together. It's really a big mess. So yeah, you probably don't want to do that very often. Let's talk about differentiation. It's really easy. These are essentially big polynomials, and we know how to take derivatives of very big polynomials. So if the sum of c sub n x minus a to the n has radius of convergence r greater than 0, then the function f of x equal to the sum has derivatives. F prime of x is the sum n equals 1 to infinity of n c sub n x minus a to the n minus 1, just like we would have done with a polynomial. We dropped the power down and we subtracted 1. For the second derivative, we just do it again. We drop the n minus 1 and we subtract 1 to get n minus 2. Now, one important thing, you'll notice that my index for the sum is changing here. We started with 0, we went to 1, and then to 2. Doesn't actually matter all that much Because here's what happens. If you left this as 0, the first term would have 0 times the rest of the mess. Well, 0 times anything is 0. So you would just have a 0 term in your sum. So not the biggest deal if you forget to change these indices. But you also don't need those 0 terms. They don't do anything. And so here's an example. I have f of x equal to the sum n equals 0 to infinity of -1 to the n x to the n. Now, importantly, -1 is a constant. So -1 to the n is also, in each term, is a constant. Okay, it's whatever it is. It's either -1 or +1. So when we take the derivative here, I drop the n from the x and subtract 1. I don't have to do anything with the -1 to the n because it's just whatever -1 is a constant. And when we take the second derivative, same thing. I drop the n minus 1 and I subtract 1, and so you can see my derivatives. All right, so now we have to talk a little bit about integrating, and that's going to be kind of fun. So let's take a look at it. All right, the last thing we have in this section is some integration. Works basically the same way. If f of x is the sum, then the integral of f of x is the sum n equals 0 to infinity of c sub n. And you'll notice, what did we do? We add 1 to the power, just like we would with any polynomial, and divide by that new exponent. Don't forget your plus c there, your constant of integration. That would be good. And here's the important thing about both integration and differentiation. Derivatives and integrals of these things have the same radius of convergence as the original. So that's very nice. So let's put our integration and well, actually, we're going to put a derivative to use here, not so much the integration. Let's identify the function. Here's my function. F of x is n equals 0 to infinity, -1 to the n, x to the 2n plus 1, all over 2n plus 1. If you write out this series, first term is x, and then a minus x cubed over 3 plus x to the 5th over 5, and so forth. Now, the reason this works out really nice is let's take its derivative. Its derivative is just 1 minus x squared plus x to the 4th, because all those denominators keep dropping out when we take a derivative. And this is just a geometric series with first term 1, and with constant with r value of -x squared. So we can say then that f prime of x is just 1 over 1 plus x squared, because remember, a geometric series always converges to a over 1 minus r. So with the negative, we get a plus x squared. Why is that important? Well, because now our series looks like something. Or, well, the derivative series at least looks like something. And we can integrate that something. We know how to integrate 1 over 1 plus x squared. In fact, we know it so well that it is just the tangent inverse function. So we get tangent inverse of x plus c. And since that's the integral of the derivative, it gets us back to the original function. So that nasty looking summation all works out to be just an approximation for tangent inverse. And that's kind of fun. So there you go. There is section 9.7. Good luck. Have a wonderful day.